Ever wondered why an AI might conclude that ice cream sales cause drownings? It's a classic case of confusing correlation with causation, seeing a link where none truly exists. Today, we're exploring a groundbreaking framework that teaches AI to distinguish real cause and effect relationships from mere statistical coincidences. This isn't just about smarter predictions. It's about building models that understand the world in ways that align with physical reality. Let's start with the core concept, a causal graph. Think of it as a map of relationships between variables, where each node represents a factor, like temperature or sales, and edges show how they influence one another. But here's the innovation. This system doesn't rely solely on the AI to infer these connections. Humans can actively refine the graph, embedding domain knowledge to guide the model. It's like giving a detective a checklist of suspects, while still letting them follow their own clues. So how does this framework actually work? It begins by generating an initial causal graph, but AI isn't perfect. It might latch onto spurious correlations, like thinking a shadow causes a headache. To prevent this, users can define constraints using attention masks, digital filters that block the model from learning misleading connections. For example, if you know ice cream sales shouldn't directly affect drowning rates, you can explicitly tell the system to ignore that link. Now let's break down the engine of this system, the causality-aware forecaster. Built on a transformer architecture, known for its prowess in handling sequential data like time series, it uses a stack designed to dissect complex patterns. Imagine multiple layers of transformers, each specializing in different temporal scales. One layer might detect short-term fluctuations, like daily weather changes, while another uncovers long-term trends, such as seasonal climate shifts. This dual-layer approach lets the model balance immediate dynamics with overarching structures. But how does it process data? The system first segments time series data into smaller, manageable chunks. Think of it as breaking a long video into individual frames. Each chunk is then converted into tokens, digital representations that capture both numerical values and categorical information. Numerical data is normalized to a 0-1 range for consistency, while categories are encoded using specialized embeddings. Missing data. No problem, special tokens flag these gaps, ensuring the model doesn't misinterpret absence as presence. Here's where the magic happens. The model uses gradient-based causal discovery. Gradients in this context act as sensitivity metrics, showing how much a variable's change impacts an outcome. By analyzing these gradients, the system identifies which connections are statistically robust. For instance, in a brain imaging dataset, it might pinpoint how activity in the prefrontal cortex directly influences decision-making regions, rather than just correlating with them. This process mimics how scientists validate hypotheses through controlled experiments. The results? This framework outperforms existing methods by 12.8% in predictive accuracy, and correctly identifies the timing of causal relationships 98.9% of the time. In healthcare, it could help researchers untangle how a drug's dosage affects patient recovery, accounting for confounding factors like diet or genetics. In climate science, it might trace how carbon emissions in one region trigger feedback loops in ecosystems thousands of miles away. So next time you see a headline linking two events, remember, true understanding requires more than observing patterns. It demands unraveling the mechanisms that drive them. And now, AI is getting closer to doing just that. Thanks for watching. Hit subscribe for more deep dives into the science shaping our future.